Alright guys, let's take a look at your warm-up. For your warm-up, it wants you to calculate fog and goff. I'm telling you that f of x is 4x minus 9, and g of x is x plus 9 over 4. Go ahead and copy down the problem, and then I'm going to go ahead and divide my workspace into two sections. The first thing I want to do is I want to find fog, or f of g of x. Remember guys, this is all about function composition. Well, for fog, I would start with g of x and plug that into my f function. So I'm going to take this g function and I'm going to plug it in to my f function. So what I'd have is 4, open parentheses, x plus 9 over 4, and then minus 9. And now I'm just going to do some simplifying techniques. I notice that I have a 4 right here in the numerator and 4 in the denominator. 4 divided by 4 is 1. So I can just replace that with just x plus 9 minus 9. And then I also notice that positive 9 minus 9 is 0, so that leaves me just x. So fog is x. All right, now let's do goff. In order to do goff, I'm going to do g of f of x, so I'm going to start with my f function, and I'm going to plug that into my g function. So what I'm going to have here is 4x minus 9 plus 9 over 4. I noticed that my negative 9 plus 9 is 0, so that's going to leave me 4x over 4. And I also noticed that 4 divided by 4 is 1, so that will leave me 1x, or just x. So my value for fog is x, and my value for goff is x also. Now I'm going to come back and revisit this because this is a very special situation, and you'll understand what this situation is after we finish today's lesson. So just know that I'm going to revisit this because there's a special relationship when you get function composition. You end up with x and x. All right, with that being said, let's go ahead and take a look at what our essential question is for the day. Your essential question is, how do we determine inverses of relations and functions? What makes math so special is the ability to undo an operation. I mean, you're taught very early that the inverse operation of addition is subtraction, and you know the inverse operation of multiplication is division. Well, we're going to actually define how we find the inverse of any function, because in math you have to have the ability to undo it. So your vocabulary is inverse function, and the way that we represent an inverse function, or the symbol that we use to represent the inverse function, is f to the negative 1. That's an exponent, f to the negative 1 of x. And just know that you will have a quiz on Wednesday, and your next test will be on Wednesday, November the 11th. All right, let's go ahead and jump right into this, and I'm going to give you a couple of slides of notes. The first one starts off with an important box. And this is basically the definition of inverse relations. If you have two relations, they are inverse relations of each other if and only if one relation contains the elements BA, whenever the other relation contains the elements AB. What that basically means, guys, is that if you have a relation, and a relation is just any set of points, ordered pairs, the inverse of that relation would simply be where you swap the position of the x and the y's. For example, if I tell you that I have a relation f with the points 3, 2, 4, negative 6, negative 2, 11, and 5, 5, then simply the inverse relation would then be 2, 3, negative 6, 4, 11, negative 2, and 5, 5. It is very important that you notice that you don't change the signs on your ordered pairs. You just simply change the order, or swap the order. The x becomes the y becomes the x, but you do not, under no circumstances, change the signs. And so that's how you define the inverse of a relation. Let's take it up a notch, and let's talk about how we describe the inverse of a function. For example, let's say that I wanted you to graph the following function and its inverse. Well, the first thing I'm going to do is I'm going to make a little t-table, and I'm going to just use these points negative 2, 0, and 2, and I'm going to evaluate these 3 points in my function. So what I'm going to have is negative 1/2 times the absolute value of negative 2 plus 3. The absolute value of negative 2 is 2. 2 times negative 1/2 is negative 1, plus 3 is 2. So that gives me the point negative 2, 2. All right, the next number I'm going to evaluate is 0. So negative 1/2 times the absolute value of 0 plus 3. Absolute value of 0 is 0. 0 times negative 1/2 is 0, and 0 plus 3 is 3. So that gives me the point 0, 3. And then finally, I'm going to evaluate 2. So negative 1/2 times the absolute value of 2 plus 3. The absolute value of 2 is 2, and 2 times negative 1/2 is negative 1, plus 3 is 2. So that gives me the point 2, 2. Now, if I were to graph this function, so 0, 1, 2, 3, 1, 2, 1, 2, 1, 2. All right, so then if I were to graph this, my first point would be negative 2, 2. The next point would be 0, 3. And the next point would be 2, 2. And so that would be my value, and then I'm going to see if I can make a line here. I don't know if it's going to let me. Let me see. Oh, I guess it's not. I thought that I could. Oh, wait, there we go. There we go. Ha. So there, and then there. So there is my function, not the inverse, just my regular old function if I were to map that out. Okay, all right, so then I can use the definition that we just had a while ago on the last slide to find my inverse. Whoops, that doesn't make any sense, does it? Let me change that right quick. All right, how do I change it? All right, let's go back to there. All right, so the way that I would find my inverse would be simply to change the order of these ordered pairs. So then I would have 2, negative 2, 3, 0, and then 2, 2. So if I were to plot these points, I would have 2, negative 2, and then 3, 0, and then 2, 2. And then I'm just going to graph this line, this function. So I'm going to have it going this way, and then it going this way. And then I'm just going to draw my little arrows to signify that, yep, that does keep on going. But what you see here, guys, is that my function, my original function, is in black, and my inverse function is in red. Now, here's a very special characteristics of functions and inverses, and you probably can see it, but it involves symmetry. If you remember, guys, we studied symmetry, and that you could talk about a function being even or odd symmetry. Even symmetry is when the function is symmetric about the y-axis. Odd symmetry is when the function is symmetric about the origin. Well, there is some symmetry with inverses. If I were to plot with a dotted line the y equals x line, that would go right through the origin, right on through. And if you notice, if I were to fold these two graphs on that green dotted line, or the y is equal to x line, they would actually map on top of each other. So they are symmetric. In fact, that's what I'm going to write here. If you have f of x and f the inverse of x, they are symmetric about the line y is equal to x. And that's what's special about it. It has that symmetry there. So that way you can look at a graph and be able to spot out its inverse by looking at if it's symmetric about that y is equal to x. All right, let's look at another problem. All right, now, here's the thing about your graphs. You can use the horizontal line test to determine if the inverse of a relation will be a function. Now, here's something I want you to notice, that all of these graphs do pass the vertical line test. If you remember, the vertical line test was a test where you drew vertical lines, and as long as each vertical line only touched the graph in one spot, then it was a function. So as you can tell, I'm going through here, and each one of my vertical lines only touches my graph in one spot. So therefore, all of these are functions. There's no denying that. The question is, are the inverse functions of each one of these also functions? I'm sorry, I should say, are the inverses of each of these also functions as well? So that's where the horizontal line test comes into play. So I don't want you to get the two confused. You only use the horizontal line test to determine if the inverse of a relation is a function. And so you do it just like the vertical line test, but this time we're going to draw horizontal lines. So if I draw a horizontal line right here, you notice it only touches it in one place. But if I draw a horizontal line here, notice it touches my function in two places. So therefore, the inverse is not a function. Okay, it can only touch it once. All right, like right here. If I draw horizontal lines, I notice that it only touches it in one place. So yes, the inverse is a function. All right, again, if I draw horizontal lines, yes, it is a function. If I draw horizontal lines, then yes, its inverse is a function. If I draw horizontal lines, yes, the inverse is a function. All right, but right here, it hits in two places, so the inverse is not a function. And then also here on G, it hits twice, so the inverse is not a function. And then finally for H, it almost looks like it's going to pass until I go right there, and it hits it in 1, 2, 3 spots, so the inverse is not a function. So remember, use the horizontal line test on a graph to determine if the inverse of your relation is also a function. All right, let's keep on going. Let's look at another example. Consider the following function below. Question A says, is the inverse of f of x a function also? Now, the best way to do this would simply draw a sketch of it and see if it passes the horizontal line test. So if I notice this is a quadratic, I know it's a quadratic function because it has a degree 2. And if you remember from your previous math course, the vertex of this quadratic would be at -3, -5. And then I also know that this is going to open up because of the lead coefficient being a +1. I know that the end behavior is going to be up on both sides. So if I were to draw a rough sketch of this, I would have -3, -5 as my vertex, and my quadratic would be opening up. Now, the reason why it doesn't really matter that my graph is exact is because I can quickly use the horizontal line test and prove that for part A, the inverse is not a function because it does not pass the horizontal line test. All right, so now what I'm going to do is part B. I'm going to show you algebraically how we can actually calculate the inverse. So here's my original function, f of x equals x plus 3 squared minus 5. The way that you find the inverse is all procedure-based, just steps. What we'll do first is just rewrite f of x as y. So we just know that f of x and y are interchangeable. They mean the same thing. The next thing I'm going to do is I'm going to swap the y and the x around. Because remember, that's what you do with inverses. You swap the order of the x and y. So my y is going to become the x, and the x is going to become the y. Once I do that, now I'm going to solve for y. So to solve for y, I'm going to add 5 to both sides. So I'm going to have x plus 5 equals y plus 3 squared. I'm going to do my inverse operation to get rid of a square. I'm going to take the square root, but when I do so, I need to make sure I put plus or minus. And so then that's going to give me plus or minus the square root of x plus 5 is equal to y plus 3. And then to finish solving this for y, I'm going to just subtract 3 from both sides. So I'm going to get -3 plus or minus the square root of x plus 5 is equal to y. And then now that I've got it solved for y, I'm just going to replace that y with my symbol for the inverse. So my inverse function would be negative 3 plus or minus the square root of x plus 5. And I could separate this into two functions, guys. I could have negative 3 plus the square root of x plus 5 and negative 3 minus the square root of x plus 5. So that would be my inverse function. Now, another way that I could prove this is by simply graphing, and that's what I'm going to do for part C, is to graph both the f of x function and its inverse on the same spreadsheet, and hopefully it will be symmetric about that y is equal to x line. So I'm going to pause for a minute and load up my graphing calculator. Alright guys, I've got my graphing calculator pulled up, so I'm going to start by putting the original function in my graphing calculator. So I'm going to do open parentheses, x plus 3, close parentheses, squared, minus 5. And so there is my original function. And so now what I'm going to do is I'm going to plug in my two inverse functions. So the first one is negative 3 plus the square root of x plus 5, and then hit enter. And so there that one is. And then I'm going to go ahead and do the other one. So that was negative 3 minus the square root of x plus 5, and then there is my other one. And then I just want to double check and make sure, but if I were to let's see if I can get the right one, that one. If I were to actually draw the y is equal to, maybe I should do it in green. Let me undo that. In green. Alright, if I were to graph the y is equal to x line, right there, and if you notice, I know it looks kind of weird, but if you notice, if you were to take this piece of paper and fold it on that green dotted line, those two functions would line up perfectly. So you can easily see that that is the inverse function of the original function. So the red and the black function is the inverse function of the blue function. So perfect. All right, let's look at one more example. Alright, so here's the last very important concept that I want to teach you, is that two functions, f and f inverse, are inverse functions if and only if f of f inverse is equal to f inverse of f is equal to x. So what's interesting about inverses is the fact that if you want to verify that a function and another function are inverses of each other, you can prove it by doing function composition. And that's what's so special about function composition, and also about the warm-up that we did. So what it's saying is that if I do my function composition and I end up with x, that is proof that they are inverses of each other. So if I wanted to prove that these two functions were inverses of each other, what I would do is I would have to find f of g of x and g of f of x, and if both of these values equal to x, then that's the proof that they're inverses of each other. So let's prove it. So for f of g of x, I'm going to start with g of x, and I'm going to plug it into my f function. So I'm going to have 2 times x minus 3 over 2 minus 3. I notice that the 2 divided by 2 reduced to 1, so that leaves me x minus 3 plus 3, that was a little miswriting on mine, and then the negative 3 plus 3 cancel to 0, so that just leaves me x. So that is true. Fog does equal x, but you've also got to show that Goff equals x also. So let's do that one also. So this time I'm going to start with f, and I'm going to plug it into my g function. So I'm going to have 2x plus 3 minus 3 over 2. I notice that the positive 3 and the negative 3 cancel to 0, so that leaves me 2x over 2, and then 2x divided by 2 leaves me 1x. And sure enough, both Fog and Goff equal to x, so therefore, that's the symbol for therefore in math, therefore, g of x is the inverse of f of x. and that's the proof, that's the justification that you would need. All right, that's it for today's lesson. If you need to review this, by all means, rewind it and play it again.